Hello and welcome to CO 442642 Graph Theory. Today we'll be talking about Thomassen's theorem. So this theorem is about list coloring, which we talked about last week. To remind you about list coloring, in list coloring, a generalization of coloring, we're talking about list assignments, L, which is an assignment of lists L of V to the vertices V of a graph G. A k-list assignment is an assignment where all the lists have size at least k. And L coloring is a coloring phi, where phi of v is in L of v for all v in v of g. And a graph G is k-list colorable if G has an L coloring for every k-list assignment L. So we went over these definitions last week when doing list edge coloring, but here I'll remind you again because now we'll be talking about list vertex coloring. And the list chromatic number of a graph G, denoted chi L of G, is the minimum k such that G has an L coloring for every k-list assignment L. And list chromatic number is also known as choosability or choice number, but I'm going to use list chromatic number, the more modern term. So that was list coloring. Now here's the question for today. What if we want to list color planar graphs? So as you may know, for coloring, as we discussed planar graphs, we have the four-color theorem that the maximum chromatic number of planar graphs is 4. And we'll be talking about that a little bit more in the rest of the week. But the question we're going to talk about today is what is the maximum list chromatic number of planar graphs? So what do we want to list color? What are some bounds? Maybe stop and pause and think about some obvious trivial upper and lower bounds. All right, now that you're back, well, an obvious trivial lower bound is that it's at least 4 since K4 is planar. It has to be at least what it would be for ordinary chromatic number, and that can be shown to be at least 4 considering that K4 is planar and needs 4 colors. What about a trivial upper bound? Well, it's at most 6 since planar graphs are 5 degenerate, right? So you can greedily even list color planar graphs. So if you're given a list assignment, you just greedily color, deleting the vertices of degree at most 5 to get an ordering, and then greedily color reverse of that ordering. So that's at most 6. So here's the question that was asked when actually list coloring was introduced in the 70s by Ardos, Rubin, and Taylor, and they conjectured that 4 is not the correct number, that there exists a planar graph with a list chromatic number at least 5, that somehow they're different. So we talked about last week a little bit how list coloring and coloring are different, and here they're saying even for planar graphs. So that the four-color theorem does not hold for list coloring. So that would be a very nice conjecture, but they also made a second conjecture, that 5 is actually the right number, that every planar graph has list chromatic number at most 5. So a very pretty answer. It's different, it's at least 5, but also it's different from the trivial one, it's at most 5. So these were these twin conjectures of Ardos, Rubin, and Taylor from one of the papers introducing list coloring. And then what happened? Well, they remained open throughout all the 80s until the early 1990s, when Margit Voigt, she showed that there actually exists a planar graph with list chromatic number at least 5. Constructed one on a couple hundred vertices. So I won't show it to you, but uses somehow smaller gadgets, smaller graphs that you then glue together in ways to force that it doesn't have a list coloring from the prescribed set of lists. So this answered the first of the conjectures of Ardos, Rubin, and Taylor in 1993, and lo and behold, the next year in 1994, Thomassen actually proved the other one, that every planar graph has list chromatic number at most 5. So this was quite surprising as people thought this would be quite hard and really didn't have much idea of how to do this, but here we have this very pretty, beautiful theorem and proof that we'll be doing today by Thomassen showing that it is at most 5. So let me just say a little bit about that. How do you prove that there exists a 5-list coloring? Just generally, not even for planar graphs. But, well, for planar graphs, if you know about the 4-color theorem, or the 5-color theorem even, you would think the 5-color theorem is easy. There's different proofs of the 5-color theorem that planar graphs are 5-color, but one of them is via identification. So maybe you do a little discharging, you identify some neighbors of a vertex. And identification just does not work for list coloring, unfortunately, because the two vertices may have different lists. So you can't, even though you can identify them and keep it planar, it's not clear what list of colors the identified vertex should get. So identification generally will fail for list coloring. So what is so easy, the 5-color theorem for planar graphs can be done in an undergrad course, is hard because identification doesn't work. But there's a second proof of the 5-color theorem, namely via Kemp chains, where you flip the colors of the neighbors so as to make sure that two are the same. And that proof also does not work for list coloring because the Kemp chains don't work for list coloring. It's not clear that you can flip these A-B colored components because maybe for a vertex that's colored B, maybe A isn't in its list. And so you can't do these switches that were so useful when we were just doing, say, ordinary edge coloring, or if you wanted to prove the 5-color theorem. So what should we do? So this eluded people for quite a while because it wasn't clear what techniques, what methods should you use. And the key, as it turns out, is to make the whole thing much harder. So to prove something stronger. So this is, one of the few times you'll really see this, but it's been used in different places now, but it's incredible. The idea that in order to prove a theorem, you make your life harder. You prove a stronger statement in the hopes that that statement is both true and more easy to prove. And how do you do this? So the idea is for the purposes of induction. So I'm going to get to that statement. So what statement do we have? What is Thomassen's stronger theorem? Well, it's quite a doozy, but once you see it, the theorem will really be quite nice and easy to prove in some ways. It almost tells you how to prove it. So here we go. Here's the statement of the theorem. So I'll reveal a little bit at a time. Let G be a connected plane graph. So it'll be plane graph. We'll just assume it's connected. It makes the proof slightly easier. And let C be the boundary walk of the infinite face of G. So since you're a plane graph, and plane means embedded here, recall. So if you're embedded, there's a face that's infinite. And so we'll let C be this boundary walk of this infinite face, the unbounded face, the outer face, if you would. So that's G and C, and we'll let P be a path on at most two vertices in C, and maybe P is just empty. So I have G, C, and P, and I'll do a picture in a moment. But now what? Now I'm going to assume I have this list assignment. And I'd like to say, well, okay, I have a 5-list assignment, and we color, but well, that would just be the normal kind of theorem, and not using C and P. But now I'm going to make my life harder. I'm going to have fewer colors in the list of vertices in C and P, as follows. So when your vertex P is in big P, the path, we'll have it only have one color. So we'll view the path as pre-colored. For the vertices on C that aren't in P, we're going to assume they only have lists of size at least 3. So they have not as many as 5, but they have more than one. So they have 3 choices. And then the ones inside, in V of G minus V of C, well, they'll have at least 5. So it's almost like a 5-list assignment, but where the outside is 3, except for this pre-colored path on at most 2 vertices. And to assume, to get a coloring, I of course need to also assume that the 2 colors of the path are different. So that's equivalent to saying G of VP has an L coloring. And if I assume all that, then the theorem is G has an L coloring. So if I have this weird kind of 1, 3, 5 assignment, then I can actually get an L coloring. So that implies the Thomassen's theorem in the weaker form, because you could just have P be empty, and then the list would all be size 5, and that would be fine. And you could just apply this again if you're not connected to each component, and that would work fine. So that is Thomassen's stronger statement. So again, here's the setup with a picture. So I have a graph G. I'm embedded in the plane, so I didn't do the embedding, but you can kind of imagine there's stuff inside. I have this outer face. Now here I've drawn it like it's a cycle, but it might be not a cycle. It might have cut vertices. And then I have an edge P. Now maybe it's only one vertex, maybe there's nothing. But here I draw it as it's an edge, P1, P2 on the path, and it's pre-colored, so I didn't give the coloring, but say like 1 and 2. And then the rest of C has a list of size at least 3, and the inside have a list of size at least 5. So this is our setup. So now what are we going to do? Well, we're going to proceed with the proof. And the nice part is it just kind of, the statement almost tells you how to do the proof. And that's the point, of course. He engineered kind of the proof first and then found the right statement to work with the ideas. But in this way, it's really, it's considered to be a proof from the, quote, book. The book of, if there was, a universal book of mathematical proofs, this would certainly qualify as one of them for being so nice and elegant and short. So here's a proof outline. We'll let G be a counterexample with V of G minimized. So we take a minimum counterexample, pretty standard. And now what are we going to do? We're going to do, well, one thing, we're going to assume that v of p is just 2. We could just do this. We can just pick one of its neighbors on the cycle and pre-color it from its list, different from the current color. If there's no vertices, we can pick out 2. So we could just do that. Let's just assume, without loss of generality, that v of p is of size 2. And let p equal p1, p2. And I'm going to do kind of different reductions. So there's really not quite a finish to the proof. The whole thing is by reductions using minimality to do color. So really, in a sense, it gives an algorithm. But there's kind of global reductions, which should remind you from Brooks' theorem. So one will be here, if G has a cut vertex, we'll do something, kind of glue colorings together in a way, but not gluing because that doesn't quite work in list coloring, but we'll talk about that. Similarly, we'll also do a global reduction when C has a chord, when there's a chord of the outer face, once we've gotten it to be 2 connected. So those will be our 2 global reductions, and then we're going to do some local reduction. So they're only going to need 1 to work in all the cases, and that goes like this. We'll pick a vertex V on C that's next to P, kind of on the outer face. We're going to delete it, and we're going to remove 2 carefully chosen colors from the neighbors of V that are not on C. So that doesn't make quite a lot of sense to you now. It will later at the end when we show a picture and we go through the details. But this is just the outline. So there's some global reductions, and then there's kind of a little local reduction around the path, pre-colored path P, that lets us make progress. And to keep up this kind of induction or minimality, to keep these conditions of the statement true. So that's also the nice part about Thomassen's theorem. It gives a nice quadratic time algorithm to actually find this coloring if you work through the details of this proof. Let's go through these reductions one at a time. So the global reduction. First one, that G has a cut vertex. So that is G1 intersect G2 is V, G1 union G2 is G. So we get this picture. And we might as well assume without loss of generality that say P is on the side of G1. So it could be V, but it has to be kind of living on some side because it's an edge. So we get this picture. And now maybe stop and pause and think, what would you do in this case? How can we use Thomassen's more inductive statement to just kind of easily reduce this case, even though it's list coloring? So stop and pause. So now if you're back, what do? Well, unlike Brooks, you can't just say, let's get a coloring here, get a coloring there, and glue them, because you need to know that they agree on V, and you can't maybe do that permuting trick that works so well in Brooks. But what we can do is this trick. We color them in order. So first we say by minimality, delete the G2, G1 has an L coloring phi, right? I mean, you're just throwing away extra stuff, so it's a subgraph, so we can get a coloring phi, but what that's really doing is extending the pre-coloring of P, of P1 and P2, to the whole of G1. And what does that mean? It gives you a color on V. So I won't write that as a detail, but it gives you a color, and now what I do is I turn to G2, and I think of that as, okay, now I want V to have this specific color, and I want that to extend to an L coloring of G2. Well, what is that? We view V as a pre-colored path on one vertex. We call it P prime, and we extend it to G2. And then together, these create an L coloring of G. So it's this, color G1, then color G2, and that works because we're allowed some bit of pre-coloring. So you're beginning to see how the pre-coloring is helpful here. So instead of needing to permute to agree maybe on small cuts, we can instead say, well, if we get to assume some amount of it is pre-colored, then we can do extend, extend. And sure enough, that's going to be our idea for the next one. So when C has a chord, we have the following picture. We have U, V, and we can assume again without loss of generality that P is inside of G1. So what we do here, probably don't have to pause the video, I just said it, it's the same trick, right? You go by minimality and you say G1 has an L coloring phi. So you delete G2, you get coloring then on U and V, and they're different because you keep the edge in G1, but then I keep the edge also in G2, and then I extend it, the coloring from U and V, which we'll call P prime now, out to G2. So we have colorings of G1 and colorings of G2. Very nice, right? This pre-coloring. So this, now we've seen we can get rid of cut vertices, we can get rid of chords, all by, or at least chords of the outer cycle. So you see how it had to be kind of the outer cycle. If there was some 2 cut in the middle, well, I guess that would also work because then we could make it the infinite face if we wanted. But really the chords of C is very nice. So that's what we're going to do. And now what? We're just to have to finish. So what good is having this cut vertex and this chord gotten rid of, right? So again, it's kind of this marriage of reductions, right? So we know if we got this statement, by adding this pre-colored path, we can assume that we indeed get rid of cut vertices and chords. But then where does like the list of size 3 on the boundary come in? Well, that's to do with this local reduction. So we're going to have one last trick, one last reduction to finish the proof. And it's going to go like this. Let V not equal to P2 be a neighbor of P1 in C. And let C1, C2 be an L of V minus L of P1. So here's the picture. We have P1 and P2, they're outer face C. Now C is actually really a cycle at this point because you don't have cut vertices. And remember, C is chordless. And now we're going to look, so that it's a cycle, so there have to be some vertex beyond P1 that's not P2. Let's call that V. And now we're going to choose two colors, C1 and C2, in L of V minus L of P1. Right, so what does that mean? Well, remember, because V is not in P, it has at least 3 colors. But then there's nothing said that they couldn't be intersect L of P1. So P1's pre-colored, but that color can still appear in the list of V. However, there are at least 2 colors that aren't that color. So let's take those two, C1 and C2. Okay, so now what? Well, now we have C1 and C2, and what are we going to do? I mean, you can stop and pause, but if you haven't seen this trick before, it's very hard to spot. But it comes from this use of the 3 colors, the 3-5 disparity. So it goes like this. We delete V, so we let G prime equal G minus V. And let's name the other neighbor, right? It's a cycle, this outer cycle C. Let's call that V prime, the neighbor not P1. That's the neighbor of V in C. And what I'm going to do is I'm going to now change the lists. So I delete V, and mostly I'm going to keep the list the same as they were as L of W, but I'm going to have L prime of W be L of W minus the colors C1, C2 if W is in N of V minus V prime. And there, it's a little tricky how I said it because what about P1? Well, P1 doesn't have C1 and C2, so don't worry about P1. But basically you can think I'm removing the colors C1 and C2 from the list of neighbors, and they have to be inside, not on the outer face, because importantly, the graph is chordless. The cycle is chordless. So we've removed these, and now you see what happens. We've deleted V, so we get a smaller graph. And now the question is what happens with the list sizes and so on. Can we kind of imply induction, or minimality rather, and then extend back to V to get a contradiction? So marinate on that for a bit, but I'll move on. So here's another picture with the vertex deleted now. So let C prime be the outer face of G prime. And now I've kind of deleted V. And you don't really know how the rest goes. If you assume the graph was a triangulation, then there'd be triangles and there'd be kind of edges, but maybe not. So those neighbors could have edges. They could be adjacent, or maybe not. So I just kind of have this amorphous picture where I've deleted it. But there's some things you can note. So what can we note about this new graph G prime? Well, since G is 2 connected, G prime is connected, right? If you delete a vertex in a 2 connected graph, you get a connected graph. So that's good because we had assumed, even though we didn't really have to, that the graph was connected in our assumption of the statement. So G prime is at least connected, great. We're going to keep P the same, so P will be pre-color. We haven't done anything with that, so we'll have P, G prime, and C prime. We have to check the remaining conditions. So let's think about the other conditions on L prime. So what else? Is L prime at least 3 for the vertices on the boundary of V of C prime minus V of P? So why? So maybe stop, pause, and think to yourself why this is. So maybe it's obvious to you, or maybe just kind of formalize it a little bit. So why are these vertices on the boundary of list size at least 3? Well, what is the boundary? The boundary is, there's kind of the neighbors of V that got exposed, but there might be other, if you don't assume triangulation, other vertices that also got exposed from the inside, and then the original part. Well, everything on the inside had at least 5 in L, and you lose at most 2 colors, so it's going to have at least 3. So we don't have to worry about the inside. You just have to worry about the outside. Is it true that anything in C, which had 3 colors, or 4, lost 2 of them and got too low? No. Because, as we said, if W was in N of V minus P1 V prime, so if you lost the colors C1, C2, then you actually have to be in the interior since C has no chord. since we proved that nice chord reduction. So that's where we're really using it. So everything inside has 5, and so they might lose 2, but they go down to 3, so they keep up at 3. So very good. So things on the outer bound, the new outer boundary have at least 3, but you should also check that the things inside have at least 5. So this would be v of g prime minus v of c prime. Sorry for the little typo. So do the things inside have at least 5? Well, stop. Why? Think about this again, formalizing in your head. Why do the vertices in the new interior have at least 5 as their list? So, give it a reason. Well, here's the answer. Since if W is n of v minus n of c, then W is in v of c prime, right? So if you were kind of a neighbor of W, a V that was in the interior, then you get exposed, right? By the deletion of V in planarity, you end up on the new outer face. So anything on the inside, they had 5 colors. If they lost colors, they automatically get pulled to the outside. And so we don't have to worry about them. And so they're at least 5. So that concludes that part, that we've established, L prime of P is unchanged. It still has a coloring, so that's fine. You have 3 on the new exterior and 5 on the new interior. So you can satisfy all the old conditions. So we're almost done with the proof, right? Because by minimality of G, there exists an L prime coloring phi of G prime. So that's a typo again, that should be G prime. So where are we? Well, now we are left with finishing this proof. So we have a coloring, we just have to give a coloring to V. So maybe again stop and think, what color do you give to V? So here you have to be a little bit careful. You have to let phi of V be one of the 2 colors C1, C2 minus the color of V prime. So here's why we use the 2 colors, why we go down from 5 to 3, why we remove 2 colors in the first place. So we pick 2 colors, and we remove them from the other neighbors of V. So that's good, so we don't have to worry about that. So it's 2 options, 2 choices to get. Now those choices were also chosen not to be from P1, so we don't have to worry about that, but we didn't remove them from V prime. So now we actually have to avoid the color that V prime gets, but it only gets one of the colors, at most one of the colors, C1, C2, so we can pick for V the other color and get the color. So this is the real key. We wanted to remove 2 colors, but not from that other neighbor V prime. Do you see why? Because if you remove colors from V prime, then it go from 3 down to 2 or 1 or whatever, and it would be too low. So we have to keep the old boundary intact, and so we have to actually then remove 2 to provide for the fact that we have to avoid the other one at V prime. So we remove 2 from the inner, and that's why you get 5, 3, 1, this nice pattern. So we need we need to go from 5 to 3 for the 2 color choices, and then you see why we need 3 to 1, because we need 2 colors, C1, C2, that aren't from P1. And also note that this proof works even if V prime is P2, so if you triangle, it doesn't matter. You just, again, avoid the color that is P2 in that case. So a very nice inductive proof. It all comes together, the stronger inductive statement. We realize kind of this, if only we didn't have chords, we could do this trick about removing colors from the inner neighbors if you could avoid the chords and the cut vertices. And so we rig the list sizes, all the conditions, to perfectly kind of match the proof. And we present it as if then it's this nice, truly inductive statement, but it's kind of built out of this, and it just all comes together to work. A real proof from the book. So that concludes today. Next, with the rest of the remaining week, we'll be talking more about coloring and list coloring, planar graphs and graphs on surfaces. Until next time, see you then.